Greetings. I welcome you all to the next lecture of this course, wherein now we will be focusing on lithium-ion battery recycling. And presently, we have seen different categories of batteries that are available to us for our use. And the advances in modern technology have pushed the researchers to develop various sources of energy storage, and lithium ion batteries have been one of the most important categories of batteries, most versatile batteries that have changed the way we look at our electronic devices. So having said that, lithium ion batteries are being used by most of the common electronic devices, and right now we are not considering the single use batteries. The utilization of lithium ion batteries have seen drastic changes, and not only in the areas of application, the extent to which we are using it. So this also means that at some point of time we are going to experience the loss of materials when we are not recycling the spent batteries. So now we are going to discuss about the recycling of lithium ion batteries, considering its enormous and ever growing utilization. So we've just noted that one of the most versatile categories of batteries is lithium ion batteries. Some key applications are: basically laptops. We have tablets, cell phones, mobile phones, and cameras. These are common applications, but the paradigm shift comes when we are looking at electric vehicles and the automobile sector. It's actually changing everything, electric vehicles and automobiles. This means that we have wide range of applications of the LIBs, lithium ion batteries, which means now we have the distribution within LIBs, life of LIBs. We would like to write it like this: shorter batteries, and shorter by mean we are just looking at the life, smaller devices. This could be used for 2 to 3 years. When we look at larger batteries in terms of life, or we have larger applications, bigger devices, basically we can have 5 to 10 years. Nearly 250 kilotons, and this time now we are actually now talking about the mass. 250 kiloton of battery waste, LIB battery waste, has been produced in 2020. So we know that this weight has increased because the production itself of LIBs is increasing. So production of LIBs is increasing, and we know that compared to other devices, LIBs have relatively lower life. We are not saying that it is very less, but compared to other batteries, it is relatively lower, which means the batteries would get dumped very quickly, and the application production of LIBs is increased. Similarly, application of LIBs is increasing. So this means this value is going to go up in the upcoming years. Now we will also like to classify our LIBs based on different types of materials. Classification of LIBs based on different cathodic materials, because anodic material is usually fixed. So we'll just write anode is usually carbon, and this carbon is present in copper foil, and aluminium can be used in the cathode foil. So carbon is the most common anode material. So we have different categories: LiCoO2, which is basically LCO type battery. We have LiMn2O4, LMO type battery. Then we have LiNix, MNY, CO1 minus X minus Y, O2. This is NMC or NCM type of batteries, NMC type of batteries. We have lithium, NIX, COY, ALZ, O2. That is Z, and this is 2. So this is NCA type of battery, and we have a different category altogether: LiFePO4, PO4. This is basically LFP type of batteries. So different categories based on cathodic materials. Anode is carbon. Variation comes when we are looking at different cathodic materials. Now one might want to wonder, why do we have so many different types of cathodes? So people have been exploring different cathodic materials to basically improve the performance of the battery. So charge discharge cycle, power supply, all of those properties, battery properties, people have been trying to explore and improve. To improve a battery performance, they change, let's say, the cathodic material, and due to this we have a very wide category of lithium-ion battery itself. Now let us just look at where we are standing. We are looking at e-waste, and a small segment of those e-waste is the batteries. Within battery segment of e-waste, we are looking at lithium-ion batteries, and within lithium-ion batteries we have so many different internal categories. So one has to think about how to recycle these lithium-ion batteries in general, so that one can deal with lithium-ion batteries properly. For that matter, if it is possible to recycle all of the batteries together, it would have been a lot more easier, but the composition fluctuates a lot across the batteries. So lithium-ion batteries themselves have many different cathodic materials, and these are important to deal with because so many valuable materials are readily seen: lithium, cobalt, manganese, nickel, aluminium. At times we also have iron and phosphorus if you are looking at LFP type of batteries. So reutilization of battery mass for battery applications is what people are now trying to target. What can be done is basically pyrometallurgical and hydrometallurgical operations can be done to generate the spent cathodic material as a renewed cathodic material. So whatever chemical composition has been changed, let's say some fresh material can be added or some other chemical procedure can be performed, so that the spent battery mass can be redirected towards the battery applications, if not directing the material for other applications. So reutilization of battery mass for battery applications is what people have been trying to explore. And this comes when we are looking at safe methods of battery dismantling. So we have discussed how we should be handling batteries, but lithium-ion batteries are important to dismantle before we go ahead for the recycling process, because the chances of explosion in lithium-ion batteries is relatively very high. So safe handling of batteries is very important. We'll be discussing about this now. Dismantling of batteries. Safely. Dismantling of batteries safely is very crucial. So what we can do is high speed shredding. Or cryogenic operations. Or thermal treatment. Now every method has its own advantage. So high speed would mean that the spent batteries are directly charged into a shredder, which is shredding at very high speed, so that the chances of explosion are totally ignored. Cryogenic operation would use liquid nitrogen, and thermal treatment would require the thermal operations such that you are able to safely dismantle the batteries. Now one can think of, let's say, range of 500 to let's say 900 degrees Celsius temperature for the removal of carbon and binder. This is one way of handling the batteries. One of the important alternatives is basically the use of, let's say, 5 to 20 weight% NaCl solution. This is an alternative solution to dismantle the batteries for let's say 24 hours. So what it really means is the batteries can be immersed in such a solution for 24 hours to discharge, to safely discharge. And this can be followed by various types of drying procedures. So one can think of air drying or vacuum drying, so that the batteries are completely dried before they are processed further. So dismantling would come later, only after one has ensured that the batteries are safe enough to be dismantled. This is very crucial, because it has been observed that when we are not practicing safety measures, these batteries tend to explode, and it can cause harmful effects to the recyclers who are trying to handle these batteries. So safety is very important while we are looking at these hazardous materials. And we know that, of course, let's say lithium, manganese, nickel, cobalt and other elements are present for us to recover, but safety should be the priority with which we are able to conduct our processes. Now, what are the materials that are present in a battery that we are going to discuss now? So, if you look at materials present in batteries, we will be looking at electrolyte, that could be nearly around 10%. We have separator, and we are talking about in weight percentages. Housing, which is basically casing, that could be around 17%. Anode foil, we know this is copper, nearly about 7%. Cathode foil, this case it would be aluminum, 4%. Anode and cathode, anode is around 18%. This composition can change with battery material, battery types that we have been discussing. So this is just a generalized composition, it can change from battery type to battery type. Dimethyl carbonate could be an electrolyte. So if we have separator, we can have polyethylene. Housing could be plastics or stainless steel or other materials. Anode foil is copper, cathode foil is aluminum. We have graphite and cathode materials. We already know what elements would be there, but element wise, cobalt, nickel and manganese, and can change. Some of the key references for this are now, what are the key pre-treatment routes? We have seen how we should be dismantling our batteries, but essentially we are still waiting on what we should be doing as for the pre-treatment. So following the procedure that we have been following can help, or we can think of using some other pre-treatment routes also. So we'll look at that. Suppose we have spent LIBs and we have safely done the pre-treatment, which is discharging and dismantling. So the first pre-treatment is discharging and dismantling, very important. This will be followed by thermal treatment, let's say. So we are able to safely remove two segments, anode. So anode for further processing, and we also have cathode. But this cathode, we can do something beyond just the collection. So we can go for comminution so that it becomes ready for further applications. Cathode material for further recovery. Anode is directly separated by thermal treatment, we've already seen. So let us say 500 to 900 degrees Celsius treatment can help us in removal of the carbon material from the black mass itself. It is the active cathode material what we are trying to use for metal recovery. So pyrometallurgical process. We know that it is going to follow a pre-treatment and then a pyrometallurgical route. So assuming that this is done, spent LIBs will have a direct reduction smelting stage, let's say, or if it follows pre-treatment, then it is just the same thermal treatment to get a different set of products, and this gives us another set of operations. So one has to think of other processes which would basically mean going into hydrometallurgy, like leaching for metal recovery. Reduction smelting, however, can give us recovered metals and slag residue. Now slag residue would require again other processes for metal recovery. This means that essentially pyrometallurgical processes standalone may not be sufficient. It can really boost in metal recovery right at the first stage, but then one has to think about slags and the recovery from slags. So at one stage we are directly getting recovered metals, and at the same time one has to think about slag recovery. So again going into different other processes like hydrometallurgy. We will now look at some of the processes that have been described by various researchers in pyrometallurgy, what are the operation conditions, and apparently they are able to recover lithium and cobalt and other metals by following the subsequent steps like water leaching or any other different type of leaching. So pyrometallurgical operation, and we have conditions vacuum pyrolysis, 600 degrees Celsius, 30 minutes, reduction roasting, so 1000 degrees Celsius, 30 minutes, chlorination roasting, 900 degrees Celsius, 90 minutes. And we know that in all of these processes we can have some or the other alternative additions also. Pyrolysis, 500 degrees Celsius, 90 minutes. Some of the references are and we know that these processes are first step. Beyond that, one has to think about the next step operation, wherein we are now going to combine pyrometallurgy with hydrometallurgy. So clearly we are going into water leaching or acid leaching as and when whichever route is required, and we are able to achieve, let's say, recovery of lithium, cobalt, manganese and nickel depending on what we have charged in the battery mass. So now we are going to look at hydrometallurgical method, which is also one of the most important routes of recycling lithium ion batteries. So hydrometallurgical processes, when we think about that, a generalized outline we need to make. So we have spent LIBs, and we do essential pre-treatment. In this case, we must ensure that the black mass itself is very fine powder. So we know that reduction of particle size, we have a reduction of particle size, and we have also done sieving, and beyond that we have leaching, filtration, this is stage 1 of pyrometallurgy, and wherein we are doing what? We are using leach liquor for recovery. And then we are going for stage 2, which is basically purification of solution. This gives us the recovered metals. So we have metal recovery. Depending on what we had fed here, we are going to get those metals here. And of course, there is the residual solid, which one has to process separately in order to recover whatever we could not leach. If we could not leach, how are we able to recover from those residual solid? And it again depends upon what reagent we have used. So we'll be now looking at some of the important leaching operations that people have performed, and how, just like pyrometallurgy, we have seen some good pyrometallurgical operations. We are now going to look at some of the hydrometallurgical experiments that people have done and how people have recovered lithium and other important metals. And what are the operation conditions? So just like that, we have reagents, we have parameters, and we have recovery. So suppose that we use H2SO4 and H2O2. We have, let's say, 2 molar H2SO4, 6 volume percent H2O2 for 60 minutes and 60 degrees Celsius. We can have 97% lithium and 98% cobalt. And suppose we have HCl, we have 4 molar HCl, 120 minutes, 80 degrees Celsius. We can have, let's say, 97 lithium, 99% cobalt. And these are just very simple generalized experimental data that we have produced. Many researchers have explored so much using H2SO4, H2O2 combination, oxalic acids, inorganic acids, organic acids, wide variety of acids like malic acid, methane sulfonic acid, combining methane sulfonic acid with H2O2, or combining two different organic acids to recover lithium and cobalt and manganese and nickel. A wide variety of literature has been explored, and parameters have changed with every set of experiments that people have performed. So, it is important to note that hydrometallurgical processes are as good as any other process for lithium ion battery recycling, just like pyrometallurgy. So, pyrometallurgy is complemented by hydrometallurgy in that sense, and we also have bioleaching. So, looking at bioleaching, we have bioleaching of LIBs has been explored using aferrooxidans, and this is an important bacteria that is used for recovery of lithium and cobalt. Now, one might want to say bioleaching isn't as quick as, let's say, hydrometallurgical operations, and it is definitely a lot more slower when compared to pyrometallurgical operations. But biometallurgy is basically utilizing a set of bacteria that are utilizing some resources that we are providing in the setup, let's say acids or other nutrients, and they are able to recover lithium and other valuable materials from the electrode mass, the black mass that we are charging. It means these are contributing to the environment by not using organic or inorganic acids, or by not consuming large quantity of energy just like pyrometallurgical processes are usually consuming. So, they have their own advantage, although relatively very slow, and one has to critically monitor the bioleaching operations, but they have their own advantages. So, now we have seen a wide variety of processes that are present for the recovery of valuable materials from lithium ion batteries. We have seen how important it is to devise the routes of the spent lithium ion batteries, so many categories based on cathodic materials, and each material can require its own style of recycling, and people have explored so many different routes of utilizing the black mass also for the generation of valuable materials, reintroduction of the black mass as a raw material for making new lithium ion batteries, and the combination of pyrometallurgical and hydrometallurgical operations for the recovery of valuable metals, nickel, manganese, cobalt and lithium. And of course, there is the bioleaching that we have also explored. In the upcoming classes, we will be focusing on the environmental aspects of metallurgical and electronic waste recycling, materials recycling, and then we will be concluding our course. Thank you.